Hello, hello everyone. I'm glad the stream is working. So, one sec. I hope everything is good. So, today we're going to do live solving of Memo 2025. And Memo is an acronym for Middle European Mathematical Olympiad. So, yeah, okay, everything's working. Yeah, that's good. So, we're going to walk through the problems. I haven't solved them yet, but that's the aim for today. I'll just try to attempt to solve the four questions, and I don't think I'll be going to bed before I do that, so I kind of need to um, do that as well. So I'm going to be sometimes looking at the chat, but I won't be looking much, so yeah. If there's something interesting that you want, then uh, just mention. I'll be checking sometimes. Okay, so let's start with problem one. So we have, okay, one sec. I'll just post an announcement that this is happening. And yeah, okay, and we'll be going on. All right. Okay, so we have a functional equation, geometries, problem three, and problem four is NT, and problem two is combi. First one is algebra, so let's start off. Okay, I just try here, and let's start solving the question. Okay. Uh, Memo. So Memo is Middle European Mathematical Olympiad. That's um, it's going on today. They have like two rounds in this Olympiad. First one is individual. The second one is like group round. So every team, like a country, uh, participates as a team on day two. Today was day one. So yeah. Okay. I'll be sometimes checking the chat if you want to send your ideas of solving or anything. So yeah. Okay, but let's go on. So we have r plus is a set of real positive numbers from r plus to r plus, and then we know that y times f to the power, like not to the power, but the iteration of 2025 of x is more than equal to x times f of y, and we need to show that there exists a positive integer n zero such that for all n more than equal to n zero, the following is true. Well, the first thing is we need to work from this condition here. So let's just rewrite it in a more sensible way. And I think it's something like this. Y over f of y is more than equal to x over f iterated 1025 times over x. Um, we know that this is true, and we want to show that there exists such an integer such that this is always true. Okay. Um, well, what we do know clearly is that by substituting y equals, well, we can substitute y equals x, but at the same time, we can always substitute something like this. And what we'll get is essentially, and then also probably x equals f of n x. Like that's kind of how we substitute something like this. Um, then what we'll get is f to the power of k x. It's a bit annoying, but divide by f to the power of k plus 1 x. I'll call it power, but I mean iteration really. And then here we'll have obviously fn, yeah, fn x, and here I'll have fn plus 2025 x. Uh, and essentially this is like a more generalized condition from here, because usually this is a problem all around iterations, and in such problems about iterations, it's always useful to think about what's going on inside a chain of f. So it's sometimes useful to think of thing like a graph. It goes from x to f of x to f of f of x and so on. And the cool thing is that basically if you have two different components of these two oriented graphs, they don't really work together. Usually, the thing that do work together usually is just looking at each component separately. Um, so we have this thing here, and obviously this is already not too bad. So I think this might be the end of the problem might be already close, but let's see. So, okay. Well, we can always put in k equals n, of course, and what we essentially will get is that f and then n k plus 2025 x is more than equal to f of and then k plus 1 x, right? And yeah, I mean, um, yeah, so this is always true. So, for example, we know that essentially in this case, if x can be expressed as f of y, then we can say that f to the power of from this essentially we know that f 2025. Or wait, can we take yeah, we can do that. So f of 2025 is more than equal to f of x, and therefore if x equals f of y, then f of 2024 of x, which is equal to f of 2025 of y, and it's more than equal to f of y, which is more than equal to x. So this is working good. And then we also know that, oh, we do have to show that for all n more than equal to something. Um, okay, so we'll have to think about that moment as well. Okay, well, I think the reasonable thing, because of this thing here, the reasonable thing to write down would be something like, first of all, reverse the thing. So say f n plus 2025. Okay, so f of implies n and x here, and then we divide by that's the power of that x. This thing is more than equal to f to the power of k plus 1 x divided by f to the power of k power again. It's iteration, so we know this thing. And the other thing that we can introduce is essentially let's define and then say a n equals f of n x over f of n minus f to the power of n x and then f n minus 1 x. That's how we define a n. And from here we can say that looking at this thing, we can say that uh, so the right hand side is obviously a k plus 1. The left hand side is equal to, interesting, um, it should start from a 2025 plus n, then a 2024 plus n, and so on, and then a so we end at n plus 1, like this, n plus n. Yeah, so from here, yeah, that's how it works. Oh my goodness. All right. Yeah, I assume that's correct. So we do know that if we look at this thing here, um, well, this is more than equal to a k plus 1 for any k, or all, oh, for this, for any k n that are positive integers. Yeah. Okay, so yeah, okay, let's think. So in terms of what we actually had to prove, going from start, well, another thing here is that we assumed for, okay, one sec. Here we assume k is more than equal to 0 and n is more than equal to 0, I assume, right? We assume that both of them are good. Yeah, I think so. Or did we? Yeah, I think we're fine. So actually for all, and then n, well, essentially z and more than equal to 0. Okay. Okay, so we wanted to show, so the statement that f to the power of n x is more than equal to x is essentially what? Well, it's essentially f to the power of n x, well, divided by x. So this is more than equal to 1. And this thing here is equal to an times, oh my goodness, an times, well, n minus 1, and so on, times a1. And we need to show that this is more than equal to 1 for n more than equal to n0. So n 0. And now we essentially, what I did is I broke down the problem into just n plus like ans, and now it should be fairly easy to show that this is true. So, okay, let's see why this is true. But we probably want to show that the sequence is decreasing or something like that. Uh, okay, let's just paste the two conditions we have on ans. Okay, so this is what we want to show. So this is the direction we're moving into, and this is the only information we kind of have. Oh my goodness. For K, N, and Z. Okay, one sec, I'll check the chat real quick to answer any questions. And okay, uh, hey, stop. Uh, okay, F 2025 X bigger or equal to than F of X. Yeah, yeah, that's true. Okay, let's continue. Nothing in the chat. If you have any questions, just let me know and I'll be sometimes checking. Okay, So we have this thing, and this is essentially what this condition means is if you take any 2025 A's in a row, so if we write down like a sequence A1, then we write A2, then we write A3, and so on. If we take any 2025 in a row, multiply them, the product will be greater than equal to all the AKs we ever have. And the good thing about that is we already know that the sequence is bounded from the top. We just want to show that at the end it goes down to 1. So because of like greater than equal to 1 is what we want to show, maybe there's and we have everything being products. Maybe a good idea would be to define log. So say Bn is equal to log, well, any base, uh, essentially log An. And what that would mean is essentially we want to show that Bn, so what we want to show is Bn plus so on plus B1 is more than equal to 1, or is more than equal to 0. And then we also know that Bn plus, oh my goodness, plus 2025 plus so on plus Bn plus 1. So essentially, again, 2025 numbers in a row is greater than equal to B k plus 1, like this, for any bk. And that's already a bit better, again, so we're just gradually improving what we want to show. So we want to show that from certain moments, this thing is always greater than 0, and then we want to show that this thing is always greater than bk plus 1. Okay, let's see what we can think about here. So this is the point where I'll stop and I'll think a bit, and then we'll see what I can do. I mean, I have two paths right now that I can think about. The first one is just try to find a clever solution. The second one is trying to induct on 2025 or just look at least on small cases. So say not 2025 numbers in a row, but two, and explore what cases happen. So this is always a nice idea when you have something like this, just to try small cases. But I also feel like maybe I'm missing something very trivial and it's just a one-liner. So I'll think a bit more and then we'll see what I want to do. But yeah, essentially we want to show that from a certain moment the sum is always greater than equal to 0. And yeah. Okay. I think I have a little idea. So it will involve another variable. So we will involve Sn. Sn is equal to A1 plus, oh, no A1, B1 plus so on plus Bn. We want to show that Sn is greater than equal to 0. Uh, for n more than equal to n0 for some constant, whatever. And then we also know that this thing on the left-hand side is essentially s n plus 2025 minus Sn, and it's greater than equal to sk plus 1 minus sk. Okay, that seems like a step in the right direction. So we want to show that this is true. Probably right now we just have to rearrange this thing in order to get what we want. Or we can probably not even do that. 1 second, let me. Um, so yeah, I mean, this thing, sk plus 1 minus sk is less than equal to sn plus 2. Um, okay. So if we'll show that there exists a k for which this is more than equal to 0, then we look, okay, let's just do this. If there exists a k for this is more than equal to 0, then essentially what we have is that uh, if we look at Sn, then we look at Sn plus 2025, then we look at blah blah blah, Sn plus 4050, and so on, so on, so on. They all increase by a bit, and even if they were negative at some moment, they'll all turn into positive. And therefore, we know that from certain moment, just by looking through all remainders modulo 2025, all numbers will turn positive. So the only case we need to uh, solve is when sk plus 1 is less than equal to sk. If that is true, then we know that this is less than equal to blah blah blah, and less than equal to sk minus 2024. And then we know that sk plus 1 minus sk minus 2024, because the difference is 2025, should be more than equal to, for example, sk plus 1 minus sk. We cancel sk plus 1 and we get sk is greater than equal to sk minus 2024. And therefore they all should be equal. And if all of these s's are equal, this means that all bn's are 0. And if all bn's are 0, this is more than equal to 0. So, yeah, we're done. Yes, we're done. Okay. I quite like problem 1, to be fair. Is the solution clean? Is that equal? Is that true, I guess? Yeah, I think it's true. Um, okay, so problem 1. I enjoyed the problem. I think it's quite nice. The idea with logs was pretty cool. Okay, let's move on to problem 2. If you have any questions, also just feel free to ask me in the comments. I'm going to problem 2. Uh, Okay, we have an infinite square grid on which some unit squares are colored red, and a ruby rook is a piece which in one move can travel any number of squares in one direction parallel to one of the grid lines, and while remaining on red squares at all times throughout the move. So we have some red squares, and the ruby rook can travel any number of squares in one direction parallel to. So just a rook, but it's only going on red squares. And then we starting with an uncolored infinite square grid. Infinite square grid, so we don't color them, and then Alice performs the following procedure. She colors at most 2025 of the unit squares red, and afterwards she places some ruby rooks on distinct red unit squares, such that the following two rules are satisfied. No ruby rook can reach another ruby rook in one move, okay? And every ruby rook can reach every other ruby rook in 2 moves. Find the maximum possible number of ruby rooks that Alice can place during this procedure. Okay. Okay, let's think. I don't really understand the problem statement. Um, I don't really understand because if we put all rooks in a diagonal, then okay, let's make sure I understand. Infinite square grid on which some unit squares are colored red. A ruby rook is a piece which in one move can travel any number of squares in one direction. Oh yeah, yeah, no, no, I get it now. I thought that my mistake was I thought if we take like a diagonal thing, then every rook can travel to any other rook, but we also need to we do need to keep the condition though that you can only travel something like this here to here. There's a rook here and a rook here. Okay, I guess it's just let's try to bound this thing. So if we have k rooks, we do know that there's well for every two rooks thing that I just showed here, they need to have a common. Uh, okay, this looks like a very easy question. I can't lie. If two rooks, they need to have like another square to which they both can reach. And we also know that this square is unique. So, because if it was not unique, if it was the same for another two pair, so if there was a rook here that also goes to the square, we do know that no rook can reach another rook in one move, and this would reach here in one move. And therefore, this square is unique to a pair of rooks. So if there's a k rooks, then essentially, if we take, I don't choose 2 of k, I denote it usually like this. I know there's another notation, but this is choose 2 out of k, or k over 2, usually in English literature. So this thing is plus k should be less than equal to 2025 for sure. So yeah, I think that's it. I can't be 100% sure, but I think this is a strong enough bound. Probably, I'm not sure. So it's k minus 1 over 2, and then plus k, so it's just this, right? Is less than equal to 2025. So k times k plus 1 is less than equal to 4050. Okay, what we're looking at 60 times 61, no. 62 times 63, not enough. Or is it enough? 62 times 63. Okay, I can't be bothered. 62 times 63. That's not enough. 64. Okay, 63. So 63 times 64 is less than equal to 4050, and 64 times 65 is already not. So we get a bound on k equals 63. And now we just need to show that this is sufficient, but this is already pretty easy. We just put 63 on rooks in like a diagonal, 63 of them here, and then essentially fill everything here up. It should take exactly this amount of. So these are all, this staircase is the red squares, and on these diagonal is the ruby rooks, and we're done. I can't lie, problem 2 is easier than problem 1. Maybe I missed something very easy in problem 1, but whatever. Okay, we're done with problem 1 and 2. Let's go on to Geo and let's just try to not spend that much time and hop on to problem 3. But we're going at a pretty good pace. I mean, I don't know how long it went. How long we have. Okay, I found like 25 minutes-ish, 20, 30 minutes on 2 problems. So we're going in a pretty good pace. Let's just try to wrap it up in under an hour, hopefully. Yeah. Okay, let's start with this question. This is instance or config. So Should be pretty nice. Let's just go ahead and do that. Okay, we have ABC is a triangle. Its incircle is tangent to okay, this is super classical. ABC, that's a triangle. Then we have incircle ABC that touches sides BCCA and AB at points DF, PQ are points on BC such that PB equals BD. Okay, midpoint. Why did they not say midpoints of BD and maybe I got the question wrong. I'm not sure. I'll check it. QC equals CD. Maybe I got the question wrong. I'm not sure. Okay. PCE. I'll right now check it. So PCE. This thing. What? QBF. Yeah, I think I got the question statement wrong. Let me check it real quick. Let's go to Yops art problem solving mathematical Olympiads. Let's go. Okay. EEF PQ from distinct from D such that PB equals BD. PB. Oh, PB equals BD. So it's like this. Yeah, I wrote it correct. Okay, let's just check that this works. So this is P, so PCE and QBF. Okay, this looks better. Okay, nice. This was stupid. Okay, yeah, let's delete this and go ahead and solve the question real quick. Okay, I already have an idea probably how to solve this. I don't think it'll take me long to finish it up. I mean, okay, so let's start off with something very, very obvious. Probably PFEQ is cyclic, but more obvious than that is these two angles are 90 degrees. For the reasons that BF equals BD equals BP and CD equals C equals CQ. Now let's chase the angles real quick to check if my hypothesis is true, because I assume it is. So this is 90 degrees. This is 2 gamma. So this is gamma. This is 90 minus gamma, 90 minus gamma, 90 minus gamma, 180 minus gamma, gamma. So I'm correct. And another thing that I'll be correct at is that the circle has the center of the X circle. So X circle IA is the center of this big circle for the reason that it lies on perpendicular bisector to PF, as it's the bisector of PBF and BF equals PB, and the same with EQ, and the same with FE. By the way, that's probably a cleaner way to show it cyclic because it lies in three perpendicular bisectors. Anyways, yeah, and on the fourth point. Okay, this is easier to show. Okay, now what we have to focus on, we have to focus on showing and looking at this circle, TCE. Yeah. So the reason why this is true is because this equals this. So this means that if this was gamma, then this angle here was 2 gamma, and this angle here is 2 gamma as well because this can. So this is true, and the other thing that I assume will be true is that, oops, the point that all three circles intersect at lies on IAD. So we do know that this is true as well. So I assume that this is true. Of course it is. Okay, now let's have a think. I mean, was that point lying in the height or something? Right. Yeah, it does not lie. Whatever. Okay, so obviously if we forget about the circle so far, we know that D should lie on the power on the radical axis of the two circles. First circle is this one, second circle is this one, the blue and red ones. The reason is BD times DQ is 2BD times CD, which is 2CD times BD, and which is PD times CD, whatever. So it does lie on this line here. Let's just name this point X. G is not a good name for a point. I'm sorry, guys. Um, show label. Great. We're doing so far. So far, I think now is just angle chase. Um, so probably right now I'll have to angle chase to show that XFDE is cyclic, or no. Okay, now let's think that we have to show that XFDE is cyclic. The thing, if I'm not mistaken, XD is the bisector. Yeah, this is true. Uh, I think the reason is to do with Apollonian circles. This is like theory of config for point X. It's ID intersecting the inner circle. So I assume if we show that BXD equals TXC, we okay, yeah. If we show that BXD equals DXC, then we know that since there's only one point on BIA such that BXC B equals BXC, then if we also show that this point lies on the incircle, then we're done. And the reason why it's true is because when we connect PAI and IQ, these are two radiuses, so this is equal to this. Uh, oh wait, maybe there's even easier way to finish up, because then this angle here. Oh wait, yeah, no, I'm tweaking. So this angle here is equal to that one, and this angle here is equal to this one. So this is true. That lies in the bisector. And now we just have to show, so we can forget about P and Q now. We can just look at point X, look at IA. So now we rephrase the problem. We have this thing here, we have IA. So I think I'm pretty sure like 90% will be able to do it on the like on the spot. I don't remember necessarily the full proof of showing that that's true, but I think I'll be able to do it pretty quickly. Okay, so here's what we have to do. We want to show that if ID intersects the incircle at point X, then XD is the bisector of angle BXC. So here's what we probably should do. We should draw the tangent from X to the incircle and get this point here. Let's call it T, and we have to show that we know that Tx equals Td, and we want to show that it's the center of Apollonius circle. Okay, this is good. All right, 1 second. Okay, so we want to show that this is true, and therefore we want to show that Tx and Td are both tangents, and we know that Xd and the X circle I lie on 1 point. Okay, let's think. So let's add the incircle center first, then draw, this is cyclic, and then we know that if we take this point here, then this point should lie on both, because for this point k, IA is 90 degrees, because it's one middle of XD, and two, it lies on BIC, so IIA was the diameter, so that's good. And I think that's really pretty much it, because I think K should be the dumpty point, or something like that for triangle PXC. Oh, no, 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 what am I saying? Okay, we know that this is true. Okay, okay, well, let's see. Let's define the things in a good way. So we intersect IAD at point K with this thing, and we intersect it at point X in the incircle. Then we know that this angle is 90 degrees, so xk equals kd, and therefore, okay, now I see it. So when we take kix, this circle, then we know that xki is tangent to the incircle here, because, yeah, because it's on diameter ix, which is radius. Then we take three circles. This one, which is tangent here, this one, and these two. And by radical axis, if we take the point of intersection of Ki and BC, T will lie on the radical axis of all 3 points, of all three circles. And this means that since it lies on this radical axis, then we know that TD squared is equal to TX squared, or let's see how to phrase it. So TD squared should be equal to K times Ti, which is equal to TB times TC. And therefore, it is the Apollonian circle, it's the center for the Apollonian circle for triangle BDC. And then we just want to show that X lies there as well, but it lies on the perpendicular bisector to XD. So therefore, this is tangent, so these two are equal by symmetry, so we're done. This is the bisector, and we're done. Okay, we're done with this problem as well. Okay, 1 second. I'll read the chat. Yeah, maybe you can show. Well, yeah, I think what Stavros said is correct, but there's multiple ways to finish up the problem. Okay, now let's move on to the last problem. And okay, how much time? We spent like, okay, we spent 15 minutes. That's a bit much on problem 3. But okay, I'll take that. A subset S of integers called Saxonian if for every three pairwise different elements A, B, C, and S, the number AB plus C is a perfect square. And we want to prove that any Saxonian set is finite and determine the largest possible number of elements that a Saxonian set can have. Okay, let's log in and finish this problem up. Okay, so obviously we know that if we take AB plus C is equal to x squared, and then if AC plus B is equal to y squared, and if we take BC plus A, it is equal to z squared. So now we probably have to subtract. So let's assume log A is more than equal to B. Okay, pairwise difference, so A is greater than B, greater than C. And this would mean, I assume, x more than equal to y more than equal to z. This is the biggest for sure. This is the smallest for sure. Or is it? I mean, probably. Okay, let's just go off of a more than equal to b more than equal to c. Then if we subtract ab plus c and then ac plus b, we will get a b minus c, like this, is equal to x squared minus y squared, which is obviously x minus y times x plus y. I assume this is correct. One second, let me double check. AB minus AC and then plus C minus B. Okay. And similarly, B minus 1 times A minus C is equal to x minus z times x plus z. And then finally, C minus 1 times uh, A minus B is equal to y minus z times y plus z. Okay, so this should be true. So let's think, what do we have to do now? Hmm. Okay, I don't think we can do anything with the minus thing. Maybe we can also do something with the plus. So if we add 2 up, we won't get the x minus y x plus y on the other hand, but we will get uh, something like a plus 1 times b plus c, right? But again, I don't think that helps us that much. So maybe we should try to at least find some solutions. Maybe that would be a good way to go about it, or to involve some bounding. But yeah, so far it doesn't look super easy, which is good, which is good. Yeah, I don't think this will help us at all. So I'll probably delete it. Let's think what we can do instead. Hmm. Hmm. And maybe we should stop working with just three numbers and involve a fourth number because it doesn't seem that we can derive much just from three numbers. And maybe there is a reason why, like, we need to look at something else except for these three. So let's have a look. So I mean, we know that AB plus D is a square, and then we know AC plus D, BC plus D, all of these are squares. And then like DA plus B, whatever, are also squares, which is a lot of squares to be found. Yeah, this is a lot of squares. So, to be fair, I don't think there could be more than three for the reasons that there just seems too many squares, and I don't think there's a construction that works well. Not from top of my head. Not from top of my head. Hmm. Okay, let's think of an answer. So let's at least try to find for three. So okay, for three, let's assume like c equals one or something. AB plus one equals x squared, and a plus b equals y squared, and then b plus a equals z squared. Oh, c plus a. Wait, yeah, this is already pretty nice. Okay, is that it? Yeah, so just a plus b is square, ab plus 1 is square. That works. Um, so we just want a plus b equals y squared, ab plus 1 equals z squared. Okay, let's see what can we find. Okay, if z is equal to 2, 3, 1. Oh, we can't have 1 though. Okay, if z is equal to 3, 2, 4. No, z is equal to 5, 2, 12, 3, 8, 4, 6. No. If z is equal to 6, it's 7, 5. No. If z is equal to 7, it's 24, 2, 16, 3, 12, 4. Okay, so 1 second. A equals 12, B equals 4, Z equals 7. Okay, and this means C equals 1. So this works. This works. These three elements, they should work, right? AB plus C 49, 16. Yeah, this works. So we have an example, at least one. Okay. We have an example n equals 3, or s equals 3, whatever. S equals 3. But we want to bound this somehow. Okay, I assume 4 is not possible, but let's go ahead and just write it off and try to do what we have to do. So A more than B more than C more than D. And then we know that AB plus D is a square, AB plus C is a square. Any three numbers from here, well, any two numbers and then plus the third is a square. Okay, let's think. Let's have a think. Okay, so let's assume AB plus C equals x squared and AB plus D equals y squared. Then we know that C minus D is more than equal to x minus 1. So this already means like something like 2x plus 2. And this is, wait, what? This looks hella weird. AB plus C equals x squared, AB plus D equals y squared. That's all good. C minus D. Okay, let's recheck this real quick. C minus D is x squared minus y squared, which is greater or equal to x squared minus x minus 1 squared, which is greater or equal to 2x minus 1. Yeah. So therefore, since D is at least 1, then C is at least 2x. Wait, is that it? Like, I just, do I not get something? Wait. Subset of integers equals succession for every three pairwise different elements. Number AB plus C is a perfect square. For it, prove that any Saxonian set is finite and determinate. Am I missing something? Like, because if C is greater than equal to 2x, and AB are both greater than equal to 2x, so AB plus C is like greater than equal to 4x squared plus 2x, which is like greater than x squared. What? Is that it? Like, is there a mistake? Okay, guys, could you? Oh yeah, 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 for sure, for sure, for sure. 1 second. So we want to show that we have subset S of integers, and we call it Saxonian if for every three pairwise different ABC, the number AB plus C is a perfect square. And we want to show that any Saxonian set is finite and determined the largest possible. So I assume there's at least 4 elements, A, B, C, and D, and I assume AB plus C equals x squared, AB plus D is y squared. Then we subtract this from this, and we get C minus D is equal to x squared minus y squared, which I assume is true. And then this thing is more than equal to x squared minus x minus 1 squared, but this is strictly less, which means that this is at least 2x minus 1. D is at least 1, so C is at least 2x. And then A, B are more than equal to x, so this is done. This is like, this is impossible for AB plus T to be equal to x squared if A is greater than B greater than C and greater than equal to 2x. So I assume it's not possible for 4 and it's only possible for 3. Um, yeah, yeah, of course. I mean, so yeah, I think that's it. To be fair, let's just check chaos. Maybe there are other solutions. I'm just not sure that this is if I'm missing something, but this looks very stupid for P4. Like very stupid. Okay. Um, yeah, I think this. Sick. Okay, this guy did something similar. This guy did something similar. They had better bounds, to be fair. They did have better bounds, but I think mine works perfectly, right? Because this square is less than this square, so take minus one. Yeah, I think mine works perfectly. Um, yeah, I mean, this looks very, very odd familiar. Am I actually missing something, or hey Aryan? No, I'm already getting finished. I just don't see if I have a mistake or not in this question, so I don't really understand. Did I miss something, or is it just it's stupid? Because on AOPS they have slightly different, and it looks like a better bound, but um, I don't see where I'm wrong as well. Okay, this guy didn't look at AB plus C. He just looked at AB plus D, so I assume he has something different. This guy did something the same. He did the same, so I mean, yeah, again, A more than B then more than C, and then AB plus C should be X squared, AB plus D is Y squared, so the difference C minus D is pretty big, and therefore contradiction. I mean, this is like question one, brilliant, question two, mid, question, like terrible, question three was fine, and question four was weird. But yeah, I think that's it for today, so thank you everyone, and have a nice day.